Hi again. Do all functions have a Laplace transform? This is the question of the day. Let's have a look at the Laplace transform. So far we have given a few examples of such Laplace transforms, like of the constant function, exponential, the sine, cosine, and so on. And we had absolutely no problems computing the Laplace transform. But can it be that there are some peculiar functions that don't have a Laplace transform? And why can that be? Let's have a look at the integral over here. This is an improper integral because one of the two limits is infinite. This means the following. Let's start by what a definite integral from a point A to a point B really is. A definite integral is the area that is enclosed under the curve between the curve and the horizontal axis. So for example, if this function is the function e to the minus s tau f tau with respect to tau, the integral of this function from a to b is this area. Then if we drag a towards 0 and we drag b forever towards infinity, then we have obtained this integral. Now we start to think, so wait, if this function doesn't even converge to 0, if it is a function like that, as b goes to infinity, if the function is like that, if it simply increases, then it is absolutely clear that the area will be infinite. So in such a case, the Laplace transform will not exist. So for a Laplace transform to exist, this function f times e to the minus s tau should decrease adequately fast, or at least f should not increase too fast. Let's give such an example of a function that increases too fast. Let's have a look at the product of the two functions. One of the two functions is e to the minus s tau. So if I select s to be a positive real number, then this function drops, and it drops very fast. It converges to 0 exponentially, as we say. So this suppresses f to go to 0 very fast, but only if f doesn't grow faster than this exponential function. Can we write down a function that grows faster than the exponential? How about we put a square over here? There are multiple ways in which we can construct such a function, but let's do it like that. Let's just write exponential of t square. Then, if we try to determine the Laplace transform, we will have the following. And here, whatever the value of s might be, this goes to infinity. It's clear that this integral goes to infinity for the simple reason that the function inside the integral is an increasing function. As tau goes to infinity, the integral will keep increasing forever until the whole area under the curve explodes to infinity. So one thing that this function f shouldn't do if we wanted to have a Laplace transform is that it shouldn't grow too fast. And let's write it down. So the function shouldn't grow too fast as t goes to infinity. What is too fast? An example of a function that grows fast but not too fast is the exponential function. So e to the at is fine. And we'll now give the following definition. We say that the function f is of exponential order if it grows slower or as fast as this function but not faster. Let's write it down. So the definition says that a function f is said to be of exponential order gamma, gamma is a non-negative number, if there exist numbers m and t0 so that this holds. But let's focus only here, let's focus on this inequality. This inequality states the following, that this is my function f, and this is an exponential function with exponent gamma. Now this says that my function is under this curve. It can grow, but it grows no faster than m times exponential gamma t. Eventually, after some time t0, after t0, it stays below there. We don't care how the function behaves in the beginning. And then the function doesn't grow too fast. And if that is the case, we avoid that as t goes to infinity, the area grows too fast, and then the integral explodes and it goes to infinity. But is that all? Is this the whole story? Can the function, for example, behave strangely between 0 and t0? The answer is yes, it might. And we will impose conditions so that this doesn't happen. So the function is fine after t0. Let's see how it behaves between 0 and t0. Let's have a look at this example to understand what might go wrong with the function, not at infinity, but somewhere else. Let's draw a function that behaves nicely at infinity. So for example, it converges to 0. It's not fast at all. But as t goes now, let's draw it in reverse. From infinity we come back to 0. But as we go to 0, for example, the closer we go to 0, the faster the function grows here and goes towards infinity. Such a function is 1 over t. Of course, 1 over t is not defined at 0. We have been talking about time domain signals, and we've said that these are functions of this form. So we must define it at 0. If we must, let's give it the value 0. So to write the whole of it, we're talking about this function. Okay. And now we have the Laplace transform of this function is this integral from 0 to infinity. And we have explained that this integral from 0 to infinity is the following area from a to b. As we take a go towards 0 and b go towards infinity. Now I'm telling you that this integral diverges. It diverges to infinity. Can you see why? It is because 1 over t goes to infinity as t goes to 0. In fact, it goes to infinity very fast, and e to the minus s tau is not fast enough at this point, is not close enough to 0 to stop it from growing this fast that the area becomes infinite. But this is not a very rigorous explanation. Let's prove that this diverges to infinity, and the way we work to show that an integral goes to infinity is we try to lower bound it by something else, something easier apparently, that goes to infinity. Let's write it down over here. First of all, this is a positive term. We will assume here that s is a positive real number for simplicity, but you can extend it to complex numbers if you like. It is very easy. Now this integral from 0 to infinity, if we claim that it diverges because the left limit goes to 0, then it suffices to study how the integral behaves from 0 not to infinity, but from 0, let's say, to 1. And this is smaller than that because we're integrating a positive quantity, and instead of taking from 0 to infinity, from 0 to 1, the integral must be smaller. But e to the minus st, e to the minus s tau, from 0 to 1 is a decreasing function, and the most it can be is equal to 1. This e to the minus s tau is at most 1 between 0 and 1. So we are talking about this integral, and the antiderivative of 1 over tau is ln, the logarithm, the natural logarithm of tau, from 0 to 1. ln 1 minus ln 0. ln 0 doesn't exist. In fact, as tau goes to 0 from the right, this goes to minus infinity. Minus infinity is plus infinity. Therefore, this diverges. And what we have shown here is that 1 over t, this function, does not have a Laplace transform. So previously, we showed that this function doesn't have Laplace transform. And we said we can avoid such situations by imposing the condition that function f is of exponential order. It doesn't grow faster than an exponential. But what about these peculiar cases? We must assume that our functions behave nicely so that they don't escape to infinity at any finite point. This function, 1 over t, escapes to infinity, diverges to infinity at point 0. As t goes to 0, the function goes up. We don't want this to happen. We want to exclude from our analysis functions such as 1 over t, 1 over t minus 1, and other functions, even tangent of t, that go to infinity at some finite point. And on top of that, we also want to impose another assumption so that nothing else strange happens. And this is the assumption of continuity. Overall, we say that the function is piecewise continuous we say that the function is piecewise continuous over this domain from 0 to infinity if there exists time instants t1, t2 up to tn. It's like that. This is our function. This is t1, t2, let's say t3. This is enough. And our function is continuous here from 0 to t1 in this open interval. It is again continuous from t1 to t2. It is again continuous from t2 to t3, and again from t3 to infinity it is again continuous. And at these points it is allowed to not be continuous. We can therefore draw it like that, and then again like this. But it is not allowed to go to infinity. So the second condition is that all these limits at 0, t1 from the right and from the left, t2 from the right and from the left, and so on, all these limits exist and are finite. They don't go to infinity. And now the big result, today's most important result, is that if a function is piecewise continuous and of exponential order, then this implies that the function has a Laplace transform. The fact that the function is piecewise continuous allows us to integrate it from 0 to infinity. Actually allows us to integrate it from 0 up to any finite limit t uppercase. This is okay because of piecewise continuity. Then because of exponential order, we are allowed to take t to infinity. and then the function has a Laplace transform. And most importantly, there is an addition to this result. If the exponential order is gamma, then f has a Laplace transform, and the domain of the Laplace transform is the set of complex numbers s with the real part above gamma. For example, this function, it is clear that it has an exponential order a. Gamma is equal to a in our case. Why? Because this function is e to the at. It is smaller than or equal m e to the gamma t. Simply put here 1 and here a. E to the at is smaller than or equal itself, e to the at, for all t above t0. T0 is 0 in that case. And indeed, if you remember, Laplace transform of e to the at is given by this function for all complex numbers s with the real part above gamma. And this is a very powerful result. But notice here, this is very important, that we have implies. There might be other functions that might not be of exponential order, or might not be piecewise continuous, or might be neither piecewise continuous nor of exponential order, and still they have a Laplace transform. We don't care about these functions in this course, because this is a very, very large family of functions that encompasses all the functions that we will be interested in working with in this course. So there are some functions that are exceptions to this rule, but if we know, once again, that the function is piecewise continuous, PWC, which allows us to integrate to compute this integral from 0 to t, and then of exponential order that allows us to take the limit to infinity, then function f has a Laplace transform. Let's do a few examples. So example number 1. This piecewise continuous, in fact it is even continuous. It is a continuous function, and it has an exponential order gamma is equal to a. Example number 2. ft is equal to t. We know that the exponential is above 1 plus t. This is the exponential, this is 1 plus t. Therefore, it is above t as well for all t which are non-negative. Therefore, it is a function of exponential order 1. For example, maybe it's not the tightest value for gamma, maybe a smaller gamma exists, we don't care about that here, but we can tell for sure that since this function is continuous, of course it's piecewise continuous because it's continuous, then it also has exponential order gamma, therefore the Laplace transform exists. But what about more difficult cases, like the following function, like this function? Does this function have an exponential order? And what about this function over here? Then there is a simple criterion that tells us whether, that allows us to tell whether a function is of exponential order. And it goes like that. So if function f has an exponential order gamma, then for all complex numbers s with a real part above gamma, the following holds. The limit of e to the minus st f of t goes to 0 as t goes to infinity. But most importantly, the converse of this result is very important and very useful. If the limit is 0 for some exponent gamma, then f is of exponential order gamma. And we can use that now to figure out whether any given function is of exponential order. This is very useful and very easy to use. For example, take function f e to the t squared. Can this happen for some gamma? Take limit e to the minus gamma t e to the t squared. And I will leave it to you to show, this is very easy, that this is infinity. So for all gamma, for all possible gamma, whatever gamma you choose, this will diverge to infinity. Therefore, this function is not of exponential order. Another example. This one, t times sine of e to the t. Take limit, t goes to infinity, then if we forget about the sign, because this is a bounded function, and we focus only on t divided by the exponential, which goes to 0, this goes to 0 as t goes to infinity for any positive gamma, and then the other function is bounded. And we can tell that this limit is equal to 0, and therefore this function is of exponential order. And it is also a continuous function from 0 to infinity. Therefore, of course, it is piecewise continuous, and it has a Laplace transform. And the Laplace transform is defined, it is well defined for all real numbers, for all complex numbers with a real part above gamma, for the gamma we obtain here, and it is any positive gamma. So we can tell that this holds. So this much about the existence of the Laplace transform. Most functions that we will be dealing with have a Laplace transform. So in summary, what we said today is that the Laplace transform of a function might not exist for some functions. An example that the example we started with is this example, e to the t squared, and the Laplace transform doesn't exist because the area under the curve grows until it becomes infinite as the upper limit goes to infinity. The other example we gave is 1 over t, where the problem happens at 0. The problem, again, such problems might occur in the middle at some other point, like for example this function doesn't have a Laplace transform either, so we want to avoid these situations, and this is why for this situation we introduced the concept of exponential order, which prevents functions from growing too fast as t goes to infinity. And then for these situations at finite times, escape to infinity at finite times, we introduced the condition that functions be piecewise continuous. And this concludes today's lecture. Thank you very much for watching, and until next time, goodbye.